Chapter 1. The Hurwitz shell. 1. Begin with the four-square theorem and introduce n equals 1. 2. 8 units. Lagrange says every natural number is a sum of 4 squares. Start with the smallest, w squared plus x squared plus y squared plus z squared equals 1. There are 8 integer solutions, the coordinate vectors, plus or minus 1, 0, 0, 0, and their permutations. As quaternions, plus or minus 1, plus or minus I, plus or minus j, plus or minus k, the 8 Lipschitz units. But the 24 cell has 24 vertices. 16 points are missing. 3. The missing 16. They live in the other coset of the Hurwitz order, the half-integer points. 1/2 times the 4 independent signs gives the missing 16. All 16 sign choices are allowed, and each has norm 1. 8 integer units plus 16 half-integer units equals 24. Exactly the vertices of the regular 24 cell. A sum of 4 square search over integer coordinates alone never sees them. 4. Where the half-integers come from. A half-integer point of norm n satisfies the corresponding 4-square equation. Multiply through by 4, every bracket becomes an odd integer. U squared plus V squared plus S squared plus T squared equals 4n, with all 4 coordinates odd. The shell of norm n is therefore described by 2 arithmetic problems at once. 5. The parity gate. Every odd square is 1 mod 8. 4 of them always sum to 4 mod 8. If n is odd, then 4n is congruent to 4 mod 8. The gate is open. If n is even, then 4n is congruent to 0 mod 8. No sum of 4 odd squares can land there. So for even n, the half-integer shell is empty. Not rare, not small. Empty. 6. N equals 2. The D4 roots. 2 equals 1 squared plus 1 squared. 2 coordinates plus or minus 1, 2, 0. 6 position pairs times 4 sign choices gives 24 integer vectors. And 4, n equals 8, not 4 mod 8. So there are 0 half-integer points. This shell is the D4 root system, plus or minus EI, plus or minus EJ. Same count as n equals 1, completely different composition. 7. The shells stack up. Enumerate both cosets for each n, and the parity pattern is immediate. Odd n. The half-integer part appears, at exactly twice the integer count. Even n. The gate is shut, and the shell is the integer orbit alone. The tempting shortcut fits the first few shells. It is also how you get burned. 8. The missed pattern. Integer side. 7 equals 4 plus 1 plus 1 plus 1, giving 64. The obvious odd partition gives another 64 vectors. Stop there, and the ratio looks broken. 64 and 64, not 2 to 1. But 28 has a second all-odd partition, easy to miss. The 2 to 1 ratio was never broken. The enumeration was. 9. N equals 14. 14 equals 9 plus 4 plus 1 plus 0. 24 coordinate permutations times 8 sign choices gives 192. For the halves, 56 is 0 mod 8. The gate is shut. A single hyperoctahedral orbit generated by 3, 2, 1, 0. 10. The 2 to 1 ratio. Sweep every odd n from 1 to 41, enumerating both cosets each time. J of n equals 2 times I of n. No violations. This looks like a theorem, rather than an accident of small n. It still does not license the shortcut. The route to Jn runs through the odd square partitions of 4n. 11. Closing method. Enumerate all 4 square representations. Group them by absolute value pattern. Compute each orbit size from that pattern. Check that the orbit sizes sum to R4 of n. The shortcut is a guess. The enumeration is a proof.